Here we're going to look at question 11 from section 2 of the ENGAA 2018 paper. In this question we're given the following diagram of a block of mass 3.6 kilograms and its forward face, labelled X, is 1.5 metres from the end of the slope that it's on. We're told that this block is initially held at rest and then accelerates uniformly to a speed of 2 metres per second when it reaches the end of the block. The question then asks us, what is the average rate of work done by friction and other frictional forces? If you would like to have a go at this question, please pause the video now, otherwise let's have a go at it. So the first thing we probably notice in this question is that we're asked about the average rate of work done, which is a bit of an unusual thing to be asked about. It's not the kind of topic which we'd normally word like that. So what does it mean? Well, the rate of work done is just going to be the work done divided by the time it takes. So it's the rate at which work is done, which we normally wouldn't call the rate of work done. We would instead just call the power. So really what we're trying to find is the power of the frictional force acting against the block as it slides down the slope. And to find this, we're going to need to find the work done by friction and the time that it does this work over. So how are we going to find the work done? Well, the work done is just the energy which is dissipated by the frictional forces. So how about we think about the energy the energy changes which are occurring in this scenario? Initially, our block is at rest at a height, so it's going to have a potential energy. Then it's going to slide, and when it reaches the bottom, we'll take this to have zero potential energy, in which case it's going to have a lot of kinetic energy, and some of our work is going to have been done by friction. So, setting up an equation for conservation of energy, we get this, that our initial potential energy is just equal to our final kinetic energy plus the work done by friction. So if we want to find the work done by friction, we need to find the final kinetic energy and the initial potential energy. So, of course, the first thing we can do with this equation is just rearrange it. So the work done is just the potential minus the kinetic energy, and then we have to try and find our potential and kinetic energy. Now, we've already said that the potential energy of our mass is just its gravitational potential energy. So it's the magnitude of the mass multiplied by the gravitational field strength, G, multiplied by the height of our mass. So how are we going to find the height of our mass? Well, we've got a triangle here with the longest side, the hypotenuse, being 1.5 metres, and this angle 30. So if we want to find the height that the block moves down, then we can just do some basic trigonometry to find that our potential energy is going to be this, with 3.6 being the mass multiplied by the gravitational field strength multiplied by this height of 1.5 sine 30 degrees. So now we've got the potential, we can find the kinetic energy, which is a little bit easier since it's just going to be a half multiplied by the magnitude of the multiplied by the velocity at the bottom. So we have 3.6 our mass and then 2 metres per second being our velocity at the bottom, which is squared. Then working this through, we get this, because we take g to be 10 in this question, so 36 multiplied by 0.75, since sine of 30 degrees is just a half, so a half of 1.5 is 0.75, and then our half cancels out with one of our 2's that's squared. Then doing a bit more multiplication, we get that our work is just 27 minus 7.2, or 19.8 joules. Now that we've got this work, we can go ahead and try and find our time. So to find the time, let's have a bit of a think about our scenario. Now we were told at the beginning that our block accelerates at a constant rate down to the bottom of the slope. So if we've got a constant acceleration, then there might be a topic which jumps to mind, and that would be suvat. So this is going to be useful because we've got a displacement here of 1.5 metres at two different velocities. We've got rest being 0 metres per second as the initial velocity, and 2 metres per second being the final velocity, and we want to try and find the time. So, filling in our different variables for suvat, we have these here, which I just explained, and time being the one we want to find. And with these, we can go ahead and try and work out which equation we're going to have to use to try and find the time. So, that equation is going to be this one, because it includes all the variables which we have and the one which we need, t. And then we can rearrange it to get this expression for t here. Then if we substitute in our values that we have, we get that t is equal to 2 multiplied by 1.5 divided by 0 plus 2, which comes out to just 1.5 seconds. So with both our work and our time, we can find our rate of work done, which is going to be 19.8 joules divided by 1.5 seconds. Now, there's not really any particularly easy way to do this division, it's just the sort of thing you'll have to work through. I think that maybe the best tip is that 1.5 is 3 over 2, so this is the same thing as dividing 19.8 by 3 and then multiplying by 2, because you're dividing by 3 over 2 if that is useful to anyone. But the answer you should get by doing this is 13.2 watts. And this is going to correspond with answer B given in the question.